Hello, everybody. Welcome to June. Today, we're in the final week here of learning, and in this final week, it's going to actually be about complex numbers. Yeah, but you didn't see that one coming, the old A plus BI, and how it relates to polar and some of the other things we've been doing. So as the warm-up here, sketch the number z equals -3 plus 4i in a complex plane. Depending on your past teachers and experiences, you may or may not remember this, but -3 plus 4i on the complex plane, this is the real axis, this is the imaginary axis. So to plot this point, you would go 3 to the left on the real axis, 1, 2, 3, and then 4 up on the imaginary, 1, 2, 3, 4, and we get a point up there at -3 plus 4i. Then it says draw a line segment from the origin to z. So like this. Determine the general angle that represents this segment and the length of the segment. So the length is going to be the easy one. Let's do that first, because if this is 3 and that's 4, that's a 3, 4, 5 triangle just using Pythagorean theorem. So I know that the length here, which we will call r for the radius of the hypothetical circle around there, is going to be 5. The angle. So if I think about this angle right here, I'm just going to do it in degrees here. I could do inverse tan of opposite over adjacent of 4/3. Let's find out what that is. Make sure that you change your calculator into degree mode. Let's see what I'm in. Hey, I'm in degree. So second tan, 4 divided by 3, and we get 53 degrees. 0.1 degrees. Now that is, of course, this reference angle. The general angle starts on the positive x-axis and goes over here. So we need to do 180 minus 53.1 degrees, which would be 126.9 degrees. So r equals 5, and theta is 126.9. Follow up to the warm-up. The polar form of a complex number is z equals r cosine theta plus I sine theta. This is a little bit more important than I'm kind of giving credit for in the middle of this. This is actually the big learning of the day, that this is how we can express a complex number in polar form. What we're going to do here is prove that it actually does work. So use your answers from the warm-up problem to verify the result is z equals -3 plus 4i. So r is 5. Cosine theta, so that would be cosine of 126.9 plus the imaginary number I times sine of 126.9 degrees. Well, let's find out what cosine of 126.9 is. Cosine of 126.9 is -0.6. So this is 5 times -0.6 plus I times sine of 126.9. So let's change that to sine now. And we get 0.8. Distributing the 5 in, 5 times -0.6 is -3. 5 times 0.8 is 4. So we do actually end up with -3 plus 4i, that same complex number. So this is just showing you that it does in fact work. These next two parts here are going to show you kind of why it works. I'm going to give you two different reasons as to why it works. The first one involves the unit circle. So here's how the idea goes. If I think about this same ordered pair, -3 plus 4i, that went out here. It had a length of 5. What I want to do is think about if it only had a length of 1, so maybe out to there, what would this ordered pair be? Well, right now this is basically -3, 4. So if we divide both those by 5, that would be the unit circle ordered pair. So this unit circle would be negative 3/5, comma 4/5, with a radius of 1. We could kind of think of this as negative 3/5 plus I times 4/5, thinking about the unit circle with the x value being here, the real term negative 3/5, and the imaginary term 4/5 I. And then if we multiply all this by the magnitude 5, kind of similar to what we've done in past chapters, it would look like this, and it would FOIL out to be that value. So if we take the unit circle order pair and multiply it by the radius to kind of scale it to how big we want it to be, we can get the point that way as well. Now negative 3/5 is actually the cosine of that angle, because 3, 4, 5, 3/5, and this would be the sine of that angle as well. So this is kind of showing you why it does work. Okay, so here's another way, in case that way it didn't suit you. You might remember that with vectors, the order pair x comma y was equal to r cosine theta comma r sine theta. So if we have an x comma y of negative 3 comma 4 out here, this can be obtained by doing r times the cosine of theta for the x value. So r cosine theta would be that, and r sine theta would be this. But what does that have to do with imaginary? Well, this is the real component, and the y value is the imaginary component. So this r is in both of those. If we factored out the r, it could be written like this: r times cosine theta comma sine theta. And then if instead of writing it as a vector, we express this as the real component, and that is the imaginary component of a complex number, we'd end up with cosine theta plus I sine theta, putting it in that form instead. So that's two reasons as to why it works, or maybe you just understood already why it worked, but this is the formula you're going to be using to solve the problems on the next page. There is a shorthand for this, so this whole idea of r times cosine theta plus I sine theta can be abbreviated r times cis theta. Okay, good luck on the problems on the next page. Email me with questions.